Hello, in this video we are going to practice some alpha carbon chemistry. Now if you look at this molecule here, we have an alpha carbon on the left and another one on the right. The one on the right contains alpha protons. So under basic conditions we can deprotonate it to form an enolate, or we can do it under acidic conditions to form an enol. And in each of those cases, it transforms this alpha carbon into a nucleophile, which can then be utilized to attack a variety of electrophiles. For example, if we want to do a crossed aldol addition, then we can use a base to form an enolate. Then the enolate is going to be able to attack the carbonyl carbon. Then we end up forming the aldol addition product. Okay. Once we form the aldol addition product, we can let it undergo aldol condensation. For example, if we do it under acidic conditions, then we are going to generate an alpha, beta, and saturated carbon, which is stabilized by conjugation, because now you can see the alternating double, single, and double bonds. Okay. This compound can then undergo what is called 1,4 conjugate addition. 1, 2, 3, 4. If we use an enamine in a process called stock-enamine synthesis. But how do we generate the enamine? Well, we know we can transform a carbonyl, the way we learned earlier, into an enamine if we use a secondary amine, the presence of an acid, and then we remove water when we apply heat, which then transforms the carbonyl into an enamine. The enamine is going to help us to do 1,4 conjugate addition, where we can utilize the lone pairs here on the nitrogen, push those electrons there, and this is going to attack that position, and these electrons are going to go here, and that breaks the pi bond. Under acidic conditions, that alkoxy group is going to pick a proton. So in fact, let us see what is formed as an intermediate. So we form this compound, OH, and we have a double bond here. Then we connect these two where the nitrogen is, and this is connected to the tert butyl group. Okay, and in fact, under acidic conditions, this compound here, this functional group, is going to undergo tautomerism to regenerate the carbonyl, and this also undergoes hydrolysis to form the carbonyl. So the product will actually look like this. So that is the product that we form when we do this 1,4 conjugate addition. What other reactions can we achieve with the alpha carbon chemistry? Well, there are a lot of other reactions, but another one that we learned is we can be able to do halogenation under acidic conditions. And that is going to install a halogen in the alpha position. If we try to do that under basic conditions, like if we use sodium hydroxide and a halogen, then that ends up forming mixtures of products, that is monohalogenated, dihalogenated, and even trihalogenated. So the best way is to use excess of the halogen, and when we use excess of the halogen, we are going to form a trihalogenated compound, which is going to cleave this position. So we call that a haloform reaction. So in this case, it's going to form CHCl3, which is chloroform. So this is a haloform reaction. This forms chloroform. And because it's cleaving that bond, we end up transforming our starting material into a carboxylic acid if we follow it with the use of protonated water. So the water is going to attack that position, and then that's what breaks this bond here, and we form chloroform. Thank you for watching.